Hi there, welcome to Algebra 2. This is Big Ideas math version of a curriculum, and this is chapter 1.1, Parent Functions and Transformations. The essential question for this chapter section is, what are the characteristics of some of the basic parent functions? And what we will learn in this chapter include identify families of functions, describe transformations of parent functions, and describe combinations of transformations. So let's get to it. Okay, before I get into example one in the book, it says to identify function families and parent function. Well, what is a parent function? And it's stated here in example one, so we can't answer a question if we don't know what is being asked. Parent function is the most basic function in a family of graphs. So for example, the line y equals x is as basic as you can get for a linear equation. The y-intercept is 0, slope of 1. That is the parent function. If I change anything, such as the slope, make that 2x, okay? Now the red line's the parent, the blue line is a family member of that function, of that family of functions. Okay, it's a member of the family of functions linear. The red one is the parent function, the most basic. And if I did this again, if I said y equals x and then change the y-intercept to say +3, then the green line here is just shifted up 3 units, and the y-intercept is now 3 instead of 0. So it's parallel to the red parent function, but it's a shift up. So functions can be shifted, and they can be translated, and they can be stretched or shrunk. And those are all in the family of the parent if you do any of those operations. So that's the definition kind of a parent function. The red line here is basically the parent function, and the others are in the family of functions, but they are transformed in some way. So that's what parent functions mean. So let's get rid of all these now. And let's start over. Okay, so that's the definition of a parent function as far as linear goes, but every type of function, be it a quadratic or an absolute value function, or cubic or cube root or square root function, they all have parent functions, and they all have families of functions that you can transform the parent. Okay, so now it says to identify the function family to which f belongs. Compare the graph of its parent function. So this is f of x equals 2 times the absolute value of x plus 1. And I'm going to put that in my Desmos calculator. 2 absolute value x plus 1. So I'm going to put that here. Y equals 2 absolute value x. And what was the rest of it? Plus 1 outside the absolute value bracket. Okay, so if I put the parent function in here, that would just simply be the absolute value of x. Okay, so the parent function is this black function here, and the purple one is the one that we were given. So as you can see, they're both V-shaped. So they are absolute value functions. And so this family of functions, it says identify the function family. It is absolute value. And let's discuss the transformation here. So this 1 plus 1 right here outside is a shift up. So the y-intercept, instead of being 0, it is 1. And the 2 out in front makes it get steeper. So notice these lines are not parallel. If I got rid of this 2 up here, that purple line is now parallel to the black line. Okay, so if we put a 2 in front of it, that stretches it, and it makes it get larger faster. So those are the 2 transformation changes to the parent function: a shift up and a stretch. Okay. Okay, so let's talk about other terms for review from Algebra 1. So remember domain and range. I don't know if I can write in here or not. I can't. So let me go back to here. Okay, so remember that if you have a domain and you have a range, you have points, x comma y. So for example, this point right here is the point over 0 up 1. That's the point x is 0, y 1. So the x is the domain and the y is the range. And I always try to get my students to remember this by alphabetical order. In the alphabet, x comes before y, so x comes before y in the ordered pairs, and domain is before range because the letter D is before R in the alphabet, so therefore it's D comma R, domain comma range. So the domain is all x values. So if I look at this function here, it's going to the right forever. That's what this arrow means. It's going to keep going out. I can put 5 in for x, 6, 7, 8, 9, 10 to infinity. And if I go left, it's going to go left forever and ever and ever. So the domain is the set of all reals. And we use a letter R for that with a double something like that. Okay. Actually, it's not like that. The line goes through. So it'd be like this, and then another line through like that. So that's the set of all reals. Okay. That means it goes to the right forever. It goes to the left forever. But now when we're talking about the range, then that is all values of y. Well, y is up here, so it does not go any lower than right here, and that's where y equals 1. So the range is when y is greater than or equal to 1. Okay, so range is up, down direction, and domain is left, right. Okay, so there's a little bit of review on domain and range. Okay, example 2, graphing and describing translations. Okay, so let's stop right there, review translations from pre-algebra, algebra 1. And a transformation means to move something. Change the size, the shape, or the position or orientation of a graph is a transformation. A translation is simply a shift. Move it right, move it left, move it up, move it down. Do not change its shape, do not rotate it, do not flip it. Translation is just a shift, moving something in one direction or the other. So example 2 says to graph g of x equals x minus 4 and its parent function, then describe the transformation. So I'll do that in Desmos, graphing the function g of x equals x minus 4. Now keep in mind that's just the name of the function in function notation. G of x just simply means what is y when x is a number that we plug in. So if this said g of 3, let's stop and talk about that a moment, function notation. So if this said g of 3 equals, then you would substitute in 3 everywhere you see an x, and it'd be 3 minus 4. So g of 3 would equal -1. So in other words, it says, what is y when x is 3? When x is 3, what is y? That's all this means. So whatever the number is you plug into the function notation, the value you get out is your y. So domain, and the calculation gives you the range, okay? And so now we're going to graph g of x equals x minus 4. Switch to Desmos, x minus 4. So I'm not going to use function notation here. Oh, I could. Let's do it, I guess. Do they allow me to? Functions, yes. That's just trig functions. So let's just use g of x equals, and it said x minus 4. I believe that's what it was. G of x equals x minus 4. There it is. The function notation. It graphed it. Get the graph or the calculator out of the way, and y-intercept of -4 and a slope of 1. Up 1. Let's zoom in a little so we can see that 3. There we go. Up 1 over 1, up 1 over 1, up 1 over 1, rise over run, rise over run. This is a linear function. So what is the parent function of a linear function? What's the easiest way to write a function? With just the variable, right? So g of x, we're going to use, it's the parent function. I'll call it f of x for the parent. And it's just simply y-intercept 0, slope of 1. So the parent function in this case is the blue line, f of x equals x. And the red line, g of x equals x minus 4, is the translated function. And the question asks us to describe the transformation. So what did we do to the blue line to get it to the red line? Well, we moved it down 4 units. So the y-intercept became -4 when it was originally 0. So we just went down 1, 2, 3, 4. And that's that constant value out here. That means shift down 4 units. Okay, so that's the answer to example 2. Okay, example 3 says graphing and describing reflections. Graph p of x equals -x squared and its parent function. Okay, so rather than just putting that in my calculator, let's graph it the old-fashioned way and plot some points. So what I'm going to do is I'm going to start with a table. So here's some x values. We're going to use -2, -1, 0, 1, and 2, and we're going to substitute them in. Okay, so a lot of students struggle when there's a negative out there, so let's do this in 2 steps. So let's just do y equals x squared first. Okay, that is going to be the most basic of the function. The negative is going to flip it. That is a transformation. And without transformation, just y equals x squared is the most basic of the function. There is the parent function, y equals x squared. Okay, so -2 squared is +4 because a negative times a negative is positive. -1 times -1 is 1. 0 times 0 is 0. 1 squared is 1, and 2 squared is 4. So I'm going to graph these points. I'm going to graph -2, 4. So if I go to my Desmos here, I'm going to graph the point -2, 4. Enter. Okay, where did it go? -2, 4. It's just off the screen. There it is, the green dot right there. Okay, and then I'm going to graph -1, 1. So then I'm going to plot -1, 1. Okay, so -2, 4 is here. -1, 1 is there. The next one was 0. 0 squared is 0. And there it is at the origin right here, the black dot. And then if we substitute in 1, 1 squared is 1. And that's the red dot here. And then finally 2, and 2 squared is 4. So there are the 5 points of the parent function. So now if I graph that, y equals, and I go to here and put x squared, then you see the green line, or the functions, the graph of the function goes right through those 5 points that we had plotted. Okay, so that's the parent function. And then we want to graph this. So how do we graph that? Well, we're just going to negate it. This means -1 times x squared. So -1 times 4 is -4. 1 times -1 is -1, and 0 times -1 is 0. 1 times -1 is -1, and 4 times -1 is -4. So really what we're going to do now is we are going to ignore the center. And now here are our x's and y's. So I'm going to plot -2, -4. So if I go back to Desmos and I plot -2, -4 and hit enter, I will have to zoom out here so I can see it. Okay, so let me get it so I can see all my points. We're only going up to 4, so I guess that'll work right there. Okay, right there. So here's -2, -4. The next point we're going to plot is going to be -1, comma, and if I go back to my table, it's going to be -1. -1, comma, -1. If I put -1 in here and hit enter, oops, I didn't have it in the right location. Let's fix that. -1, comma, -1, close parentheses, enter. So now we're going from here to here. And then the next point is going to be 0. But when I square 0, I get 0. And when I multiply by -1, it is still 0. So that is going to be shared with the other 0, 0. And then if I substitute in a 1 now, okay, and square it, and then multiply it by -1, I get -1. So it's going to be -1, comma, or 1, comma, -1. And then finally, if I substitute in a 2, I square it, I get 4, multiply it by -1, and I get -4. Okay, so there it is. Now if I graph the function, and what do they call it? I'll use function notation. P of x equals -x². Okay, so I'm going to put P of x equals -x to the power of 2. Okay, so there's the two functions. The green one was the parent. That's y equals x². Or what do we have? Y equals x². And then the other one is P of x equals -x². And as you can see, it's a reflection across the x-axis. The 0, 0 is the point where they meet or touch the reflection point or line, the line of reflection. They touch right there. -1 gets reflected over to, or -1, comma 1 gets reflected over to -1, -1, and so on. So these are all just reflections across y equals, or the x-axis, I'm sorry. So that's a reflection of the parent function green, y equals x², reflecting it across the x-axis and getting y equals -x². So the transformation is a reflection across the x-axis. Okay, example 4 says graphing and describing stretches and shrinks. Graph each function and its parent function, then describe the transformation. So the parent function of g of x, let me get my pen. The transformation of g of x equals 2 times the absolute value of x. So these brackets mean absolute value function. So the parent function would be, let's call it f of x. And that would just simply be the absolute value of x. Okay, the absolute value of x is the parent. The only thing that's happening here is we're multiplying it by 2 after. So if I did a table for f of x, here's x, here's y. Let's not call it y, so we know what table's what. Let's call it f of x. Remember, f of whatever just simply means what is y when x is a certain value. Let's just start out at -2, -1, 0, 1, and 2. So f of x means take the absolute value of what x is. Well, what's the absolute value of -2? What's the absolute value of -1? The absolute value of 0, the absolute value of +1, and the absolute value of 2. Okay, so then I'll switch colors here, and then I'll take the g of x function and say, here's x, and here is g of x over here. What is y when x is -2, -1, 0, 1, and 2 again? So if I take -2 and take its absolute value, that would be 2, and then multiply it by 2. So what we're really doing is we're just saying 2 times the absolute value of, keep putting a parenthesis instead of the bracket, 2 times the absolute value of -2. And that is going to give us our value g of x. So this should be equals 2 absolute value x. So if you wanted to do a table like that, you show the function in the middle, and then you show what you get out here. Substitute it in 2 times the absolute value of -2. Well, the absolute value of -2 is 2. 2 times 2 is 4. 2 times the absolute value of -1. Absolute value of -1 is 1 times 2 is 2. 2 times the absolute value of 0 is 2 times 0, or 0. And then 2 times the absolute value of 1, which is 1. 2 times 1 is 2. And then finally 2 times the absolute value of 2, which is 2. And 2 times 2 is 4. So these are the x's over here, and these are the y's we got over here. So what changed? They're all just multiples of what we got before. We're multiplying by 2. So that is a stretch. Okay, so think of a stretch as pulling away from the x-axis, and it makes the thing get bigger or smaller faster. And a squeeze pushes it down and spreads it out, and it makes it grow slower or shrink slower. So let's graph these two. G of x equals x squared. I will do, or 2 absolute value x, I will do it from the table, -2, 2, so just to show you that it works. So let's go back to Desmos and plug these values in. So I had the parent function first, it was 2, 2, and then it was 1, 1, and then it was 0, 0, in my parentheses. Whoops, that's an O. Okay, and then we had 1, 1, and 2, 2. Is that right? These are supposed to be negatives. So I start out with -2, 2, -1, 1, 0, 1, 2. Okay, so there's the v. So now if I just graph the function, y equals the absolute value of x. Okay, then you see that the function goes through 1, 2, 3, all 4, all 5 points. Okay, and then we're going to do the same with the other one. To save time, I'm not going to plug them in as points. You see that it's going to work -2, 4, -1, 2, and so on. That is 2 times the absolute value of x. So they called it g of x, I believe. So g of x equals 2 absolute value x. So this purple line here is the parent function, and the black line is the stretched one, if you will. Okay, it was transformed by a stretch, and it was a multiple of 2. So it's getting bigger faster. So instead of being here, this point ended up at 0.1, 2. Right there. -1, 2, and -2 became 4, where before it was -2, 2. So the y value is getting doubled. So it's growing faster. All right, let's look at the next one. H of x equals 1/2 x squared. So first of all, let's call the parent function g of x. And all we have to do is get rid of this 1/2 out in front. It's a parent function. It's a parabola. It's quadratic, x squared. The most basic parent function. Leading coefficient is 1, exponent 2, no linear or constant term. It's just g of x equals x squared. So let's do a table. Put g of x over here. Just kidding. Put x over here. And g of x over here, which would be our y. -2, -1, 0, 1, 2. -2 squared, -1 squared. Whoops. Let's redo that. Control R. Doesn't redo. All right. -2, -1, 0, 1, 2. -2 squared is 4. -1 squared is 1. 0 squared, 1 squared, 2 squared. Okay. H of x is the parent function. Shifted, or not shifted, but squeezed, pressed down. So I'm going to put x here, and I'm going to put h of x here. So you take the parent function, and you put this half out in front, and watch what's going to happen. So if I take -2 and I square it, I get 4. Half of 4 is 2. -1 squared is 1. Half of 1 is 1/2. 0 squared is 0. Half of 0 is 0. 1 squared is 1. Half of 1 is 1/2. 2 squared is 4. Half of 4 is 2. So look what happened. We're using the same x's and y's. 4 became 2, 1 became a half, 0 became 0. So we're dividing all the y values by 2. Okay, so if I graph this now, let's clear this last function. And let's just put y equals x squared. Okay, so that is this one here. And let's change that to green now. So click on here. I think I can change colors. Thought I could. You can turn it on and off. All right, I'm not going to worry about that right now. And then we're going to do h of x equals 1/2 x squared. Okay, so the parent function here is red. 0 squared. Let's zoom in a little bit. There's our 1. 0 squared. 1 squared. 2 squared. Okay, but over here it's going to be 0 squared divided by 2, 1 squared divided by 2, and so on. So to recap that, when our leading coefficient in front of our function is between, not equal, 1 wouldn't change it, between 1 and 0, okay, oops. If it's x is between 0 and 1, the value in front of the variable, the coefficient, if it's between 0 and 1, it's a shrink. And if it is greater than 1, it's a stretch. Okay, if you're getting on the negative side, it's a reflection and these. Okay, example 5, describing combinations of transformations. Use a graphing calculator to graph this function and its parent, then describe the transformations. Okay, so I'm going to do that. We're going to use a graphing calculator, but there are going to be different components here. This is going to do something to the function. This is going to do something to the function. And this is going to do something to the function. So this parent function, let's call it f of x. Let me do it in black, actually. Let's call the parent function f of x. Well, what's the most basic absolute value function? Because these are absolute value brackets here. Well, the most basic one is the absolute value of x. So let's graph that first. So we'll go to Desmos, and we will graph the absolute value of x. There it is. Okay, pretty simple. And then we go back, and now we're going to graph g of x. And I'll type it in as a function notation. G of x equals negative absolute value of x. So look what that did. That did one thing. And then the plus 5 inside is going to do something. Okay. Got to be inside. Okay. Plus 5. And then finally, minus 3. So what did that plus 5 do? What did the negative do? That was over here. What did the plus 5 do? And then the last one was minus 3. And what did that do? So there is the parent function red, and there is the translated function blue. So it got flipped over at the x-axis. That's what this negative did. It reflected it across the x-axis. The plus 5 shifted it left 5. So let me explain that. Let's go here. This plus 5 right here, plus 5, when it's inside your absolute value brackets or inside your operation, you go the opposite direction. So a plus 5 inside is actually moving it left 5. The minus sign flipped it. So minus flips, plus 5 moved it left 5, and then minus 3 outside is down 3. So those are the transformations that occurred. So I'm going to show you that in pieces. So if I just did the absolute value of x, that's the red one. But then if I did the absolute value of, or actually the negative, the absolute value of x. Okay, that's this green one. And then if I just did, I'm going to do it in steps now. So let me get rid of the whole function. So here was the parent function, absolute value of x. I put the minus sign out in front, and that gave me this green function, which flipped it over or reflected it across the x-axis. Now I'm going to continue. I'm going to say negative absolute value of x plus 5, and just do that component. So after reflecting it, so this is a reflection and a shift left, and then finally negative absolute value of x plus 5, and then outside minus 3 is the black one. So this might get a little confusing to you. The red one is the parent. Reflected across, that's just simply the minus sign, reflects it. The plus 5 inside the absolute value bracket moves it left 5, and the minus 3 outside the absolute value bracket shifts it down 3. So the vertex of the function, if you will, the reflection didn't move it. The shift left 5 put it here. The shift down 3 put it here. And that resulted in this function right here. Okay, so that's what all those components did. Let's get this out of the way. Okay, reflection, shift left, shift down. Okay, example 6, modeling with mathematics. The table shows the height y in feet, a dirt bike, x seconds after a jump off the ramp. What type of function can you use to model the data? Estimate the height after 1.75 seconds. Okay, so they're asking us to do a couple of things here. First of all, I'd graph these points to see what type of function it could be, to see what it looks like. And then, so 0, 8, 8, 20, 24, up until here, you could say possibly linear, possibly quadratic, but then it's decreasing, decreasing, so it's linear is gone. So those are the things you have to think about when you're looking at tables. But they also want us to estimate the height after 1.75 seconds. So 1.75 would be right here. So already I'm going to estimate it's between 8 and 20, right? Because 1.75 is between 1.5 and 2. So this is decreasing, so it's going to be less than 20, but still greater than 8. Because 1.75, that's not a negative, by the way, it's just a marker. 1.75 is between 1.5 and 2. All right, so let's plot these first. 0, 8, and we'll put this in Desmos. So let's go to Desmos and plot the point 0, 8. And I can't see it, so let me move my, there it is right there. 0, 8 is right here. The next point we want to graph is 0.5, 20. Okay, so now I'm going to have to zoom out. So I want to see the 0. I want to see the ground. Think, you know, we're dirt bike jumping here. So 0, comma 8, 1/2, comma 20. The next point is 1, comma 24. Okay, so I'm going to have to zoom out a little bit more. Bring that down. Okay, so there's 1, comma 24 right here. 20, 21, 22, 23, 24. 0, 8, 1/2, 20, 124. Then it's coming back down 1.5, comma 20. 1.5, comma 20. And finally, 2, comma 8. Okay, so there it is right there. Now let me make some adjustments here. Let me pause this so you're not watching, and I'm going to stretch this out so it's not so squeezed. We're not using much on the domain, and our range is huge. Okay, so in order for you to use Desmos, you should see what I'm doing now. Okay, so there's a wrench here. That's graph settings. So you click on that. And I want my x-axis. This says between negative 9.572. Actually, I don't need to go less than 0. So let's make that -1. See how it moved it over. And my x-axis really doesn't have to go greater than 2. So let's just go to 3. Let's change that to 3. All right, so there it is. Let me move me back over here. So we're going from 0, 8 to 1/2, 20, 124, 1.5, comma 20, and back down 2, comma 8. Now it asked us to estimate where 1.75 would be. So this graph looks like a parabola curving like so. Okay, that looks like a parabola. It's a upside down parabola, so it's got to have a negative value in front of the x. So let's try and play around with this and say, well, it's a negative x squared. Okay, and what did that do? See how that's way down there? Well, I want to move it up. I want the highest point to be 24. So let's say plus 24. Whoops, 0.4. Plus 24. Okay, so that brought our height up here, but now I have to shift it to the right. And a shift to the right is going to put, whoops, what is this doing? There we go. Okay, a shift to the right is going to be minus inside, and we want to go over 1. Okay, so now we have our function reflected, shifted up 24, right 1, but it's too wide. Well, how do we make it squeeze in this way? You want to make the number greater than 1. So let's try 2. That didn't work. How about 3? Closer. How about 4, 5, 6, 7, 8, 9. About 10. Getting closer. See how it's squeezing closer and closer as that number in front gets bigger and bigger? And it's looking pretty close right there. So I kind of found the function by playing around with this Desmos. It may not be exact yet, but it's close. Now, what the question also asked was, what's the approximate y value if x is 1.75? So I can go back to Desmos here and I can say, well, if I drew a vertical line, x equals 1.75. That's right there. Okay, so then we have this intersection point right here, 1.75. And then what you would do is draw a horizontal line, and that would be your y value. And I just clicked on it, and it told me it was height 15. So then if I click on the next one and say y equals 15, then that is where those two intersect. So it looks like we had to go over 1.75 and up 15. So getting back to this question, the height of the bike after 1.75 seconds should be approximately 15. Could be exactly, but it looks approximately to be 15. All right, so that's how you mess around in Desmos. Makes it really fun and interesting to see what changes occur when you do things to functions. Hopefully that was helpful. Okay, so that is the end of chapter 1.1. The exercise for my class anyhow, I want them to do numbers 9 through 34 and finish filling in this chart. So what I know and what I want to know is what you fill out before watching the video, and what I learned is what you put in after watching the video. So please do that and have a great day.